Welcome to today's Coastal Resiliency Lunch and Learn. Today's event is hosted by Tip of the Mitt Watershed Council and the Land Information Access Association. So my name's Jennifer McKay. I'm the Policy Director at Tip of the Mitt Watershed Council. And so for those of you who are not familiar with the Watershed Council, we're a nonprofit membership-based organization with 40 years of history protecting and improving water resources in northern Michigan. We protect, restore, and enhance our lakes, streams, wetlands, and groundwater through respected advocacy, innovative education, technically sound water quality monitoring, thorough research, and restoration actions. We achieve our mission by empowering others, and we believe in the capacity to make a positive difference. We work locally, regionally, and throughout the Great Lakes Basin to achieve our goals. Currently, we have 13 staff members and hundreds of volunteers that work tirelessly to achieve our mission. Today's event is part of a larger grant project for the Watershed Council that's funded by the Charlevoix County Community Foundation and the Petoskey Harbor Springs Area Community Foundation. The goal of that project is to help communities make more informed and comprehensive long-term decisions by clarifying current thinking on how the Great Lakes water levels are projected to change and presenting a sustainable approach for incorporating variation in future lake levels in decision-making framework. I know that today we have a number of individuals from across the Great Lakes Basin attending, which is wonderful. But for those of you who are local, this is the first step of our grant project. We intend on following up with those municipalities in Charlevoix and Emmet County to provide assistance with the partners that you'll hear from today to help you improve your master plans and ordinances to be better prepared in the future for both high and low water levels and the climate changes that are occurring and that will come in the future. With that said, I will also say we are very fortunate to have amazing partners to work with on the project. And so I want to acknowledge that we have additional funders that have allowed this workshop to occur. And I want to thank the Michigan Coastal Zone Management Program, the Michigan Department of Environment, Great Lakes and Energy, the National Oceanic and Atmospheric Administration, and the U.S. Department of Commerce. A bit of housekeeping today before we begin. All attendees will be muted throughout the meeting to avoid background noises. Throughout the meeting, you can ask a question by typing your question into the question and answer box or by raising your hand in the webinar controls. If you raise your hand, we'll call on you to ask your question, and at that time, we'll need you to make sure you unmute yourself before asking your question. We'll do your best to answer all of the questions, but given time limitations, we may not be able to do so. In addition, I want to mention today that today's webinar is being recorded and will be made available at a later date on the Watershed Council's website and a YouTube channel. So we have a great lineup for today. Today's speaker include Dr. Drew Groins, who's a professor at the University of Michigan, Dr. Guy Meadows, who's a professor at Michigan Technological University, and Dr. Richard Norton, again, a professor at the University of Michigan. So the purpose of today's webinar, as we all know, changes to lake levels and climate are forcing coastal communities to reevaluate how they manage land use, new development, and infrastructure. And the purpose of today's workshop is to provide information on how to address those dynamic challenges and build greater resilience in their communities. Throughout the next 2 hours, we'll provide a broad overview of coastal dynamics, resilience planning, how changes in coastal climate are impacting communities. In addition, we'll provide an engaging overview of scenario-based planning tools and how planners and local officials can use that data to inform your local planning efforts. And so with that, I will pass the webinar over to Leah.
All right. Hi, everybody. I'm Zach Vega. I am the community planner at the Land Information Access Association, and let me share my screen real quick. I'll be brief. I want to let us get into our speakers for today. And let me remove this. So like I said, the Land Information Access Association, or LEA for short, we are a 501c3 nonprofit based out of Traverse City. We've been working with U of M, our partners at the University of Michigan, Michigan Tech, and MAP, as well as NOAA and the Department of, EAGLE for short. I'll just summarize that. And we've been doing this work for a few years now, and I just wanted to bring up a couple of resources as if you're a municipal official, you might be interested in. So throughout this presentation, our team uses the Urban Sustainability Directors Network definition of community resilience, which is the ability of a community to anticipate, accommodate, and positively adapt to or thrive amidst changing climate conditions or hazard events, and enhance quality of life, reliable systems, economic vitality, and conservation of resources for present and future generations. So throughout this, when you hear the term community resilience, we are looking at that from a community-wide holistic approach. So right now, we just wanted to make you aware, LEA, through funding with the Coastal Zone Management Program, has matching grant opportunities. So this would be a one-to-one match. And we can work with communities to figure out exactly what deliverables you would want to get out of this. But we've sort of presented three options that most communities go for when we work with them. And those can be a full master plan update, coastal resilience master plan chapter. So just a chapter that collects a lot of the data that you'll see throughout this presentation, and then working with the community to actually get a chapter into the master plan. If you've just updated your master plan and you're not looking for a master plan related document, but you still want to have coastal resilience addressed somewhere in your municipality, we also have the option of developing an action strategy. And if you want more information on this one-to-one matching grant opportunity, you can visit resilientmichigan.org, and I'll actually show you what that looks like when you get there. So this is the Resilient Michigan website. You can go to the communities tab to see what other communities we've worked in and get samples of the plans that we prepared. If you go to the documents tab, you can see some of the resources that we've collaborated on with our partners, as well as a community sustainability self-assessment tool, and just other resources that you can use for not only coastal resilience, but resilience in general. And also, I just wanted to point out that LIAA has a podcast that we specifically target public officials for. So we have professionals from around the state that share their insights on what they're researching. And going forward, we actually just put out our first episode in a Great Lakes series featuring Guy Meadows, who you'll hear from today. And if you're interested in learning more about coastal resilience after this, feel free to check out the podcast by just going to lea.org/podcast or searching it on Spotify, Apple, or however you listen to your podcast. And without further ado, I will take up no more time, and I'll pass it over to Drew Grunwald so that we can start get going with our speakers. So thank you.
Great, thanks, Zach. And I'm going to start my presentation up. Thank you so much for the introduction and the invitation to be here. Zach, well, I can still see you, or somebody can, you guys confirm just that you can see my screen right now and my hand moving? If one person could just give a quick acknowledgement of that.
Yeah, we can,
okay.
Thank you.
Looks great. Okay, great. Thank you, folks. And thank you, everyone, for taking the time to listen in. Again, my name is Drew Grunewald. I'm an associate professor at the University of Michigan's School for Environment and Sustainability. I have adjunct appointments in the Department of Civil and Environmental Engineering, as well as the Department of Earth and Environmental Sciences. And today, what I want to talk about is the science behind Great Lakes water level fluctuations. And we're deliberately setting this up so that my talk, Professor Norton and Professor Meadows' talks all blend together to give you a holistic perspective on water level fluctuations across a range of timescales. This is the outline for my talk. It looks extensive, but it's really not. The key nuggets here are in those middle three components. I want to talk about historical water level variability on a few different timescales. I want to make sure that we leave this lunch chat with a clear understanding of what drives the Great Lakes water balance, and then talk about how that ties into the art of forecasting water levels and what current water level forecasts look like. In addition to thanking the Tip of the Mitt Watershed Council and their partners, I need to thank all of my colleagues, particularly our laboratory group at the University of Michigan. I'm very fortunate to work with an extremely talented group of students, scientists, postdoctoral fellows, most of which you see here. And when I worked for NOAA, the National Oceanic and Atmospheric Administration, I also had an extremely talented group of colleagues, many of which you see here. The data sets you're going to see would not have been possible without this group and without decades of legacy work by federal agencies on the Great Lakes. So to give you a quick frame of reference for the topic of Great Lakes water levels, I want to start out by underscoring the complexity of the Great Lakes system. And this satellite image, I think, helps to reflect that complexity. So what we're seeing here is a sort of early winter shot or late fall shot of the Great Lakes, where we're seeing all types of hydrological and meteorological processes combine. For example, on the land surface, we can see that there's a lot of snow on much of the Great Lakes basin, but there's heterogeneity or differences in how that snow is distributed across the land surface. And of course, we can also see clouds forming over the lakes, in part reflecting or correlating with a lot of evaporation leaving the Great Lakes. And these processes are taking place over massive spatial scales. The Great Lakes, as we'll talk about in a second, are some of the largest freshwater surfaces on Earth. So in fact, if we look at this table here, I've summarized the largest lakes on Earth by surface area to put the magnitude of this problem into perspective. What you see on the left-hand side of this table are the names of the largest lakes. The second column shows the country or the countries in which those lakes reside, and then either the surface area or volume of those lakes. When I highlight the Great Lakes, we see an interesting pattern, one of which is that when it comes to total surface area, nothing really quite comes close to the collective surface area of all the Great Lakes. Lake Victoria has a very large surface area, and so does Lake Tanganyika. But in terms of total freshwater surface area, the Great Lakes really take the cake. When it comes to volume, I like to make the point that the Great Lakes, Lake Victoria and Lake Tanganyika contain an awful lot of fresh water, but what I find most profound is that 80% of all of the Earth's fresh surface water, fresh unfrozen surface water, is contained in just its 10 largest lakes. There are 100 million lakes on Earth, give or take, but just the 10 largest contain 80% of all fresh unfrozen surface water. And for that reason alone, I think it's critically important that we understand how water moves through, within, and across these lake systems. So just to make sure we all have our geography set, here's a different snapshot, a map representation of the Great Lakes. The tan area represents what I'm going to be referring to as the Great Lakes Basin, or the tan area itself more specifically is the watershed of the Great Lakes, where water drains into the lakes. And then water flows through the system, essentially from Lake Superior through the St. Mary's River into Lake Huron, where it exchanges with Lake Michigan through the Straits of Mackinac, continues flowing out through the St. Clair River, Detroit River into Lake Erie, over Niagara Falls, and then into Lake Ontario, where it then makes a relatively long journey down through the St. Lawrence River out to the Gulf of St. Lawrence. A different perspective on that flow pattern is through a hydraulic profile. Same system here, where we start on the left with water flowing from Lake Superior through Lake Michigan, Lake Huron, across Lake Erie, over Niagara Falls into Lake Ontario, and then down through the St. Lawrence River. And it's important to have this perspective, in part to recognize how connected the Great Lakes are, but also how different features of the lakes, particularly the control of Lake Ontario, which we're not going to talk about too much today, affect or don't affect the rest of the system. And finally, before I dive into the science here, I want to make sure we understand how important it is to recognize that we have a lot of great information about the Great Lakes and how water levels change, where water comes from, and where it goes to. Unfortunately, there are times when media or other outlets can try to confuse the science behind this, and this depiction of the Great Lakes really does that. This came out during the time of low water levels in December of 2012 and January 2013, when record low levels were set, trying to depict the idea that we don't know where water has been going during these low water level conditions. Maybe there's some drain in the bottom of Lake Huron. And of course, we have the science to explain where water went and why water levels were low. And let's talk about that next. So first I want to give a perspective though on water level variability. It's important with a group like this just to start off by saying we are so lucky to have an extremely robust water level monitoring network across the Great Lakes. Water level gauging stations look like this. This one is actually located in Mackinac City. There are about 53 gauges like this on the US side of the Great Lakes and about half that many on the Canadian side of the Great Lakes, making up a network that can be mapped out like this. The blue squares represent US water level gauging stations owned and operated by NOAA, the National Oceanic and Atmospheric Administration, and the red squares represent gauges owned and operated by the Canadian Department of Fisheries and Oceans Canada. So together, just an incredibly robust monitoring network. And whether you're looking at water levels on a lake-wide average long-term scale or at an individual gauge, it's almost certain that the data you're looking at comes from this network. So if we take a moment to look at long-term water level records, gauges on individual lakes actually go back all the way to 1860. So if we look at the x-axis on the bottom here, we see the time range I'm showing goes from 1860 all the way up to present. The vertical axis here is surface water elevation in meters. There are breaks here in the numbers to represent the loss in elevation through the channels that connect each of the lake systems. The red line that you see is the long-term average water for each lake or lake pair in the case of Lake Michigan and Huron. Light blue dots are the monthly average water level and dark blue dots are the annual average water level. And what you can see just by staring at this, and we could spend a lot of time doing so, but just briefly, you can see that water levels go up and they go down. There are a few prominent features that we should point out though. One is the extreme variability relative to the other lakes on Lake Michigan and Lake Huron. The total variability on the Lake Michigan, Lake Huron system is upwards of about 2 meters or close to 6 feet. And we can see we've spanned that variability over the past 10 years. Another key feature is the diminished variability on Lake Ontario that you can see that started in the 1960s. Not as significant, of course, to the Lake Michigan, Lake Huron system, but a pronounced diminished variability that you can see there as well. We can look at water levels on much shorter time scales as well, and that's certainly relevant to the discussion we're having today. So this plot, don't worry, you're not missing any data yet. I'm just showing an empty plot. The bottom axis here shows time, and we're looking back at October 2012 through early November 2012, when Hurricane Sandy was not only dominating conditions on the East Coast, but also across much of Eastern North America. And this satellite image depicts that, which is sort of centered on the mid-Atlantic here, but you can see the wind patterns affecting southern Lake Huron and Lake Erie. And so what we see here first is a time series of water levels at what we call the Fort Gratiot gauge, right at the southern end of Lake Huron. I can add in water levels from Lake Erie over the Buffalo gauge during that time period. And then finally at the bottom, I can add in water level measurements in New York City during the exact same time period. So 3 water level gauges. The 2 on the top are from the Great Lakes system, and the one on the bottom is from the Atlantic coast during the storm. So two neat things to point out here. One is this rise in Lake Huron water levels during the hurricane, a pretty significant rise of over a meter or so of water being pushed up in southern Lake Huron. What I find interesting is that most of the water that was stacking up there was actually making its way through the St. Clair River and down into Lake Erie. Without that outlet, water would have stacked up even more during this time period. But then let's take a look before the hurricane at these spikes. These, of course, as you know, are seiche events, primarily wind-induced seiche events, causing water to slosh back and forth on Lake Erie. And what I want to finish with, and Guy will talk about this more, and Dick might as well, that these events have a huge impact on coastal life, erosion, and I would argue that they are of the same magnitude, if not more, than coastal tides. But the final point is they are much harder to predict than tidal variability, yet have a huge impact on coastal design and coastal life. So let's shift next and talk about what we call the Great Lakes water balance. In other words, that's an accounting of water coming into the Great Lakes and water leaving the Great Lakes. And it's helpful to start off by, again, delineating the Great Lakes basin. So the black line here represents the watershed, the boundary of all the water that comes in from the land surface of the Great Lakes system itself, excluding the St. Lawrence River. And it's even more helpful to break this down into individual lakes. So we can look at the Lake Superior Basin and its water balance, as well as the water balance of the other lake systems. So let's start off by doing that. And when we look at the accounting of water in each of the lakes, it really comes down to what we call three main components. And those components are summarized in the upper left here. They are runoff, that's the total amount of water that comes into each lake through rivers and streams. The second component is over lake precipitation. That's the amount of water that comes into each lake directly through precipitation that falls on the surface of each lake. And I want to pause there for a second and circle back to what I talked about earlier. There's really no freshwater system on Earth that has such a large exposed surface of fresh water. And consequently, there's really no system where the amount of precipitation falling on a lake or on a freshwater body has such a big impact on the water balance and on water levels. So a really unique feature. Hand in hand with that is the impact of over lake evaporation, the amount of water that is lost over time through evaporation. And so if we show the relative magnitude of those components for each of the lakes, we see some interesting patterns. For example, if we look here at Lake Superior, this bar graph is showing the long-term average flow of water through Lake Superior from each of these components. These numbers are in thousands of cubic meters per second. So for example, around 1,600 cubic meters per second of water flow into Lake Superior through runoff, while around 2,000 cubic meters per second on average of water come in through precipitation directly on the lake, and then finally around 1,400 cubic meters per second leave through evaporation. These are tremendous quantities of water. I can shift over. So these numbers describe what's happening within each basin. Of course, there's water that passes between the basins as well through the interconnecting channels, and that's what's shown on the right-hand side here. So these green lines represent the magnitude of water flowing from each lake to the downstream lake. So for example, 2,200 cubic meters per second of water on average are flowing from Lake Superior into Lake Huron through the St. Mary's River. By the time we get down to the St. Lawrence River, we're looking at about 7,000 cubic meters per second of water. So how do these components change over time? Well, if we look at long-term timescales, this graph is showing water level data going all the way back to the late 1800s. The blue dots that you see are Lake Michigan, Lake Huron water levels on the top here, Lake Erie water levels here. I'm just showing these two lakes for simplicity. The orange and green bars are showing over lake precipitation magnitudes. And they're showing anomalies, or at least they're colored to show anomalies, where green bars are above average precipitation values and orange bars are below average precipitation values. And what you can see is something that we've observed in the past, which is that for much of this period of record, water levels in blue tend to follow the variability in precipitation. In other words, precipitation across the region was really the primary driver of variability until you get to this later 2-decade period that I'm circling with my hand right here, where precipitation is relatively persistent and high across this period, but water levels plummet. So based on our understanding of the water balance, we should be able to hypothesize why that might be. And it turns out that based on our research, the primary reason for that decline, if I shift slides here from looking at precipitation to evaporation, we can see an enormous surge in evaporation during that time period that is the primary driver of the water level decline. Interestingly, since we published this work, we found that the sudden surge in water levels over the past several years is not only due to continued increases in precipitation, but also due to a rapid decrease in evaporation, much of which coincided with that very cold winter of 2014 when we had an Arctic polar vortex deformation. So to close things out, I want to talk next about how we take this understanding of the water balance and how the water balance influences water levels and put that together into water level forecasting. And before I begin, I want to acknowledge that just like when we look at historical water levels, we can look at different time scales, hourly, daily, monthly, and even multi-decadal. The same is true for water level forecasting. We can be interested in knowing what water levels are going to be like hours or days from now, months from now, and even decades from now. And what's important to recognize is that depending on the time scale of the forecast, we need to take into consideration different what we would call forcing variables. For example, if we want to know about water levels a day or two from now, or even hours from now, the primary driver might be wind speed and direction. But if we want to know water levels several months from now, the primary driver is really going to be precipitation, runoff, and evaporation. However, if we want to know changes in precipitation, evaporation, and runoff on long-term timescales, we need to know the broader climatological forces that are influencing precipitation, evaporation, and runoff. And those really come down to large continental scale air masses that move across the continent that bring major changes in air temperature and major changes in moisture. And these are actually a well-recognized summary of the major air masses that typically move across that continent. Just to give you a quick example here, maritime polar air on the right here and maritime tropical air typically differ in temperature, but they both bring quantities of very moist air to the region. In fact, over the past decade, we've seen an increase in the amount of moisture that has come into not just the Great Lakes region, but Central North America through these air masses. In contrast, this very cold Arctic, continental, polar air, and Arctic air can periodically dip into our region, bringing very dry and cold air. And so what's important to recognize is that if you want to forecast water levels on the Great Lakes over monthly and interannual timescales, you need to be able to forecast precipitation, evaporation, and runoff. In order to forecast precipitation, evaporation, and runoff, you need to be able to forecast how these air masses move, and that is very tricky science. You also, in order to forecast these variables, need to know not just what's happening in the atmosphere, you need to know what's happening on the ground. And I'd like to show this map of soil moisture, one of the most important variables dictating the rate of runoff into the Great Lakes. This was from last spring, February of 2019, when we had extensive flooding across the region. And you can see these percentiles of soil moisture ranking. This comes from NOAA, the rankings across the Great Lakes, Mid-Atlantic region. We're looking at some of the most extreme soil moisture conditions ever. Now, I just recently downloaded the most recent soil moisture profile. Despite the low rain we've been having and the heat, all that moisture is still taking a long time to drain through the basin. And you can see in the lower part of the Great Lakes Basin, conditions are at least average, and in some parts still way above average in terms of soil moisture. Importantly, if you want to make good seasonal forecasts of water levels, you have to take into consideration the amount of moisture in the soil, as well as the amount of snow that is across the system that might come in through melting. So when this gets put together, there are a lot of different forecasting systems out there and research being done on forecasts, but one of the most widely publicized and one of the most strong from a foundational perspective are those generated by the federal agencies at the United States Army Corps of Engineers, and as well as Environment and Climate Change Canada. So this is a forecast specifically for Lake Michigan and Lake Huron, generated by the Army Corps of Engineers, that takes into consideration past variability in the water balance and pushes that variability forward in terms of different water level scenarios. So just so you're clear on what we're looking at here, on the bottom axis, we're looking at April and mid 2018 through 2019, and then into 2020, and then into the future here for 2021. The black dots here represent the long-term average monthly values on the Lake Michigan Huron system. These dashes at the top represent record high water levels for each month. This black line, this continuous line, represents actual water levels on the system. And so you can see starting in January of 2020, we've been consistently, I would almost say, shattering records for each of these months across the Lake Michigan Huron system. But then importantly, here are different projections of where water levels might go into the future. The gray band represents what you could almost think of as every possible range of water balance scenario from the past pushed forward into the future. The blue line and the purple line represent two specific years, just for comparison, one of which is 2012 and 2013. In other words, if we got the same water balance sequence that we did in 2012 and 2013 starting right now, what would happen with water levels? Well, you remember 2012 and 2013 were an extremely dry period. The purple line represents what would happen with water levels if that water balance sequence repeated itself. I find this to be an incredibly useful tool for understanding water level projections over the next several months and even over the next 1 to 2 years. And then finally, there's a lot of work being done on what we would call multi-decadal forecasts. These are forecasts looking out really to the end of the century. So on this particular depiction, which comes from a tool called the Great Lakes Water Level Dashboard that synthesizes a lot of projections. On the top here, you see Lake Michigan Huron, and on the bottom, Lake Erie. The blue dots that you see are historical water levels with an average red line going through them, same for Lake Erie. And then these rectangles that you see on the right represent the range of projected average water levels in the future from a variety of studies from experts all around the Great Lakes. Some of them include Brent Lofgren at the NOAA Great Lakes Environmental Research Laboratory. Others include Murray McKay and Frank Sigleniaks from Environment Climate Change Canada, but really a synthesis of the current state-of-the-art in water level projections, average water levels. And what we see here is that there's really not sufficient evidence, and I hate to use the word evidence because forecasts don't really constitute evidence, but nonetheless, there's really not a strong claim here based on the models and how they represent the future that water levels are likely to be significantly higher or significantly lower decades from now relative to what they've been in the past. What is important, and with the research we're doing right now, is taking a look at variability over much shorter time scales on annual, monthly, and even hourly and daily time scales. It's my perspective that when it comes to design, planning, and considerations regarding zoning, and Dick Norton can talk about this more, it's those shorter time scales that are really should be influencing decisions. So a couple of final thoughts here as I wrap up and transfer things over. The first is that when it comes to understanding water levels, I think one of the most important sources of information is the historical water level record. We are so fortunate in the Great Lakes to have water level records, very robust water level records that go back over a century. And then finally, I want to underscore the point I made earlier, which is that when it comes to planning considerations, I think the big question right now is how is climate change changing the way that precipitation and evaporation on the lakes are interchanging, and to what extent is that changing the rate of water level variability compared to what it's been in the past. So with that, I will stop sharing my screen and turn it over to the next speaker. And again, thank you very much for your time and attention, and to the Watershed Council for hosting.
Thank you, Drew. Before we go to the next speaker, we do have one question that came in, and it is, are there Canadian data sets equivalent to the NOAA soil moisture levels?
Yeah, absolutely. So, Guy, I can see your face. Can you hear me right now? I just unmuted myself.
Yeah, loud and clear.
Okay, great. Great question, Lucas. The answer is yes. And Lucas, you dived into a very important point, which is that the data set I showed actually represents a problem with a lot of the data sets that are generated for this region, which is that they are of national origin, meaning that these federal agencies are almost not even authorized to share data across the border, at least display it. So another way of answering your question is both NOAA and Environment and Climate Change Canada, they generate models and data sets that extend these variables like soil moisture across the border. But when they develop the final map product, they actually truncate the data to show only the data on either the US or Canadian side of the border. And then one of the challenges we face as scientists is to stitch that all back together to tell a comprehensive story. So the short answer to your question is yes, but it underscores a really important point about data harmonization across the international border.
Great, thanks. And with that, we will move on to Dr. Meadows.
Thank you, Jennifer, and thank you, Drew. It's always hard to follow Drew. What a tremendous presentation. It's a pleasure to be here, and I thank the Tip of the Mitt Watershed Council for the opportunity. I like to also talk about varying timescales and go way back to kind of set the stage for how our shoreline responds to the types of fluctuations in water levels and wave energies that Drew was talking about. So to begin with, this amazing basin of fresh water is a relatively new feature, geologically speaking. The lakes took their present form about 12,000 years ago with the retreat of the Laurentian ice sheet, which over most of the Great Lakes region was estimated to be about a mile thick. So it's a tremendous amount of ice. Our crust of the earth is still responding from the unloading of that ice sheet, causing the northern lake levels, the terrain around the lakes to rise. But being new features, the point is the Great Lakes are very steep-sided and very deep. And the natural process is for them to broaden out, and that broadening of the basin is what we call shoreline erosion, and filling in the deeper parts of the lake. And that process has been going on for thousands of years. And it results for Lake Michigan and Lake Huron of a background erosion rate, the broadening of the basin, by about a foot a year, independent of any of the changes that humans have made to the shoreline. So keep that in mind in terms of long-range planning. The shoreline in most places will be 30 feet further shoreward, independent of lake levels, than it is today in a 30-year period. So given that fact, we can make estimates on how much sediment is transported down our shorelines. So the transport of sediment is controlled by the redistribution of wave energy. So the bigger the waves, the greater the transport of sediment. And it's also dependent on how much will be transported. So if we look at Lake Michigan, for example, in the southern basin of Lake Michigan, you see the arrows along the shoreline getting larger as we move from Grand Haven on down towards the Indiana border. And that is a reflection of the waves coming from the northwest being the largest waves over the greatest distance of water, being able to move the greatest amount of sediment to the south along that section. And that quantity of material is somewhere in the order of 100 to 150,000 cubic yards moving past any particular point. Same thing's happening along the Wisconsin shoreline. You can see the two arrows in the basin around Gary, Indiana, converging, and that's responsible for an area out in Lake Michigan called Gary Shoals, which is a large accumulation of Michigan and Wisconsin sand, unfortunately. As we move to the upper part of the basin and more to the neighborhood of the tip Mitt, we see the arrows are much smaller and they've reversed. They're moving from south to north rather than from north to south. And again, that's a reflection that in the northern part of the lake, the most severe wave conditions approach from the northwest. It's those big, long storms that have all of Lake Michigan to blow through from Chicago on up to the Michigan shoreline. The waves are huge, but the sediment transport is not as large because there is not as much available sugar sand to be transported down the beaches as there is in the southern part of Lake Michigan. So the geology of the basin also plays a major role. As Drew indicated, we've seen both the highest and the lowest water levels in Lake Michigan and Lake Huron in the last 20 years. So starting in 1986 was the previous all-time high water levels for Lake Michigan and Lake Huron. We had a secondary peak around 1997 that was almost as big as the 1986 high, and then a precipitous water drop starting around 1999, and then a 14-year period of very low water levels in the Great Lakes. And that 14-year period from about 2000 to 2013 along our shoreline. That in mind, we're going to come back to that point. And then as Drew indicated, everything changed around 2014 with the hard winter, the all that went along with that, water levels began to rise. And when I created the end of this diagram here in the yellow, I was thinking lake waters might go as high as 582.3 feet. And keep that number in mind because that is a new all-time record, surpassing the 1986 record, which has been the all-time record going back, as Drew indicated. We had this precipitous period of very low water levels, a lot of building on the shoreline, extremely rapid rises in water levels in 6 years, which is totally unheard of along the Asian coastline. Leading up to that, take a look here at a plot. The dotted lines are the total wave energy incident at the shoreline, and we're starting here in the late 1950s, and we're going for a 32-year period up here to about 1990. So this precipitous peak up here is the all-time high in 1986. So these are the events leading up to the previous all-time high water level. So I'm going to smooth out that line. This is the growth of wave energy. So as water level is rising in the Great Lakes, we're seeing more storms. Drew had a nice example of where those storms might originate from in terms of Pacific maritime air and Gulf of Mexico maritime air. But they also bring local winds, which result in an immediate effect of having wave energies increase. So if it seems like these years where we're in another high water period that waves are bigger, the storms are more frequent, that is entirely true. And this is the plot of water levels through that same time period. So the water levels are following the increase in wave energy by about 18 months. So the storms that deliver water to the basin create large waves. As Drew indicated, a lot of that precipitation falls on land as well as a lot of it falling on the water itself, but it takes a significant amount of time for that water all to reveal itself as increased water levels. Across the bottom graph is shoreline damage associated with this rise in water level. And you'll notice that in both cases, the maximum shoreline damage is aligned with the peak in wave energies and not necessarily the peak in water levels. So water levels are the enabler. They allow the waves to work at the most dangerous place, but the wave energy has actually increased by about 25% over what it is in low water years to high water years. So larger, more frequent waves are, because of high water levels, allowed to work at the most dangerous place to the beach, which is at the base of the bluff. So the shoreline is receiving a double hit during these periods of high water. Well, how does the natural beach respond to that? So when we begin at low water, as we had through that period of 1999 through 2013, it was inflated. Waves deliver sand from offshore to the water's edge. Wind blows that into berms along the shoreline, builds foredunes, and the beach is really storing that sand as a protection to the up and coming next episode of high water. But when high water does arrive, that beach, the part of the beach that we walk on that has been built up during low water, rapidly erodes and moves offshore to form offshore bars. And those offshore bars are designed particularly to trip those larger incoming storm waves that we know occur during high water level. So the beach has this natural of adjusting its above water and below water profile to be as dissipative to the new water wave environment as physically possible. There is no structure that is as a natural beach that's allowed to have the freedom to move and adjust its profile. An equilibrium beach. So given the tremendous difficulty people are facing with high water and high waves in this and under funding from the Coastal Management Program, we took the opportunity to create what we call the 80-year look at the shoreline. So we went back to the 1938 aerial photography, rectified those, and then took 4 stops between 1938 in time to the present. And our most recent photographs are 2018. So it allows individual property owners, and the website that we welcome everyone to look at is across the bottom, geospatial research, mtu.edu/coastal zone management program. And these slides will be made available to everyone. But it allows you to the individual property owner scale to go in and look to see how your property, adjacent communities, your whole section of shoreline has responded from 1938 to the present. This is an example south of St. Joe, Benton Harbor on Lake Michigan. It's an area that's heavily developed and an area that has experienced tremendous amount of coastal change. So the blue line that my pointer is on out here is the 1938 shoreline. The line here is the top of the bluff in 1938. And similarly, the blue line along the present shoreline is the 2018 shoreline and the present top of the bluff. The red hash marks here are the 30-year projection of where the top of that bluff will be based on the erosion rate over the last 80 years for this section of shoreline. So this is a very vivid example of the amount of infrastructure that is in danger along the southern shoreline of Lake Michigan. So 3 years ago, we did this for the entire shoreline of Lake Michigan. So it's available for all areas, again, down to the individual property owner. Last year, we concentrated on the Lake Huron shoreline, and this year we are beginning the Lake Superior shoreline. So this is an ongoing effort. We welcome you to explore the website and look to see how your shoreline has changed. So section of shoreline that we just looked at, but an oblique view from offshore, you can see that these are substantial structures that are in danger. In the foreground, you can see the previous attempts to stabilize the shoreline with hard engineering structures and that they have ultimately failed. You see attempt after attempt to try and prevent erosion. And you see the upper corner here, you can see the downdrift effects of what even revetment type structures produce on adjacent shorelines. So if we use the same tool here and take a look at the tip of the Mitt area, this is the area around Harbor Springs. Obviously, your shorelines are extremely stable compared to the southern end of Lake Michigan. So congratulations. This is the same 1938 and 2018 shoreline superimposed here. There's been minor changes, but again, no massive erosion like we see in the southern part of the basin. Part of that is the sand supply, and then you can see in the offshore that there are some hard structures, substrate rock structures that are helping to hold your shoreline in place. We look at the 1938 shoreline from the historic aerial photography. Very little has changed. We flip back. Similarly, if we move on to Charlevoix, for example, the same is true. Small differences between the shorelines, which is primarily the difference in water levels between the two photographs. So shorelines are extremely stable in the northern part of the lake, which is very good news. So that raises the issue of inundation versus erosion. So there's the definitions from the dictionary. Inundation is the shoreline being covered with water. Erosion is actual loss of the shoreline. So in the southern part of the lake, we saw tremendous shoreline erosion. in the northern part of the lake, the pictures we just looked at from the shoreline viewer show the variations in water levels. So the 1938 water level was about 2 feet below the 2016 water level. And now in 2020, we have actually hit that 582.3 feet, or we are up from the last photograph in the shoreline viewer, an additional 2 feet or so in water level. So 2 foot of water level rise is 100 foot of beach being inundated or lost from. And again, I think this long-term view has showed that that beach is not eroding, but is just being covered by water, where in the southern part of the lake, that is actually being eroded and is gone forever. There, one place here north of Leland, here along Christmas Cove, is an area that's been erosionally active. So it's one of the few places in the tip of the Mitt region where I could find a good example of actual erosion. There's been a lot of controversy with rebuilding the handicap access parking area to the beach here. This is the 2015 offshore image. And you can see the beach there in the center with the parking lot, and now that parking lot has been lost to nearshore erosion. Again, returning as Drew did to the latest Lake Michigan, Lake Huron water level predictions by the Army Corps of Engineers. Again, every month through this year, this is the current water level in red. The dashes are the previous all-time highs, the year that they were set in water levels. And you can see very clearly, starting last December, every month of 2020, Lake Michigan and Lake Huron has set a new record for the all-time high, again, going back to the 1860s or so. So tremendously high water levels that we have not experienced in the past. The question becomes for long-term planning is, what will those water levels look like in the future? And for a little bit of optimism, this is, again, the most recent predictions by the Corps of Engineers that came out about 2 days ago. We, the nice people up in Lake Superior, where I live, we went through this last year. We set new records in 2019 over our all-time high up until the month of October. And then we started losing water out of Lake Superior, and we are presently below last year's averages by about 5 inches or so. We're forecast to remain low through the rest of this year, and since all good things flow downhill, I'm pretty optimistic that Lake Michigan and Lake Huron might begin to have some relief next year, since water levels have dropped. Recall that Lake Superior contains 53% of all the water in the Great Lakes basins, which another way of saying that is there's more water in Lake Superior than there is in Lake Michigan, Huron, Erie, and Ontario combined. So we have a lot of water, and the fact that we are decreasing away from our all-time high last year is most likely good news for Lake Michigan and Lake Huron. We tend to build structures along our shorelines for various purposes, and they have impacts on adjoining properties. So shore perpendicular structures are most commonly of the groin type on the Great Lakes. Purpose of a groin is to trap sand on the updrift side and stockpile that sand for the owner of this property at the expense of depriving the downstream owner of sand. It's no different than a dam across a river. In fact, there's a great 20-minute video put out by the Army Corps of Engineers in the late 60s called Beach a River of Sand that makes that point. The problem with groins is once one neighbor starts doing it, it's a snowball effect where the next neighbor is then forced to do a similar project, and so on down the line until we get to the last neighbor who here in the far right decided not to do it and pays a tremendous price. So again, these structures are very difficult to get permitted, if at all, along the Lake Michigan shoreline, which is now a good thing. Harbor structures, whether they're small structures like New Buffalo or Leland, or large structures on the left like St. Joe, Benton Harbor, are essentially large-scale groins. They trap sand. The purpose for trapping sand on the updrift side is to protect the entrance channel so that it's safe for navigation. But the unintended consequences of that is to build beach on the updrift side of these structures, in both cases at the expense of depriving the downdrift side of any sediment. So the result is exactly the same. Revetments do similar things to downshore properties, but the mechanism is slightly different. With revetments, they are some form of armoring structure, shore parallel structures that are intended to pin the intersection of land and water, which is good for the homeowner that builds it, but they are far more reflective, no matter what their slope is, than the natural beach, and they deprive the natural beach of that ability to reshape itself to be dissipative. There's on the right-hand side an example of a natural beach, and then an armored beach. The main problem with the armored area is it drives the near shore sandbars further offshore. The waves that reflect off these structures, and the structures ultimately fail, not by being beaten back by the waves, but by actually falling forward into the waves. And that process is indicated here. Same is true if you have a rocky shoreline. So in the northern part of the lake here, where there is more exposed rock, again, be careful to watch where the sandbars are moving. If they're moving offshore, you might want to do some things to soften this reflection and do everything you can under low water to maintain beaches in this area to prevent this reflected wave of driving sediment offshore. Here's an example of a revetment in front of this home. It's acting like a groin in some respects. It traps sediment on the updrift side to the benefit of the neighbors to the north, but again, at the expense of the neighbors to the south. So we can learn some lessons from history. So after the to establish 45 permanent survey lines all along the Lake Michigan shoreline. And I spent my summer vacations from 1988, our first survey, through 2008, 20 years of surveying these lines periodically, sometimes multiple times per year, but at least once a year. So there's a tremendous data set available on how the beach recovered after the all-time high in 1986 and how the beach changed and responded to variations in water level. And I'd like to show you some examples of that. This is from Survey Line 1, which is right at the Michigan-Indiana border. This is what the beach looked like in 1988, right after the 1986 all-time high. The beach is all carved out. Road Commission or Corps of Engineers has dumped some large boulders. Note the stormwater drain here that's suspended into space behind the survey crew. And the beach has been scoured almost back to the road, which is across the top, and this is the stormwater drain from the road. This is exactly at the Michigan-Indiana border. During that, about halfway through that 14-year period of low water levels, this is how that beach built back. So each water levels, the beach, when given the opportunity, will come back. But each time, each cycle, the beach eats away further into the shoreline. And that's where this 1 foot per year of background erosion occurs. So the beach builds back, but it builds back with what we're famous for in Michigan, pure Michigan sugar sand. And what has been eroded away was that glacial till material that has been packed by that glacier 12,000 years ago that was about a mile thick. So this new deposit of sand, although it looks very stable and wonderful, is extremely erodible. It goes away very, very quickly. So if you show it up on the shoreline in 2008 and looked across this beach, it's about 300 feet wide. It looks stable as can be. What's wrong with building a house there? And that's a kind of a foreshadowing of what the story I'm going to tell here. This is in 2008. That is the end of that stormwater pipe from the road that was totally suspended in free air. So since these were real surveys, we actually have real data. So these are the surveys of that section of beach, starting at the top of the bluff there along the road. The 1988 survey here is this lower one along here. And then we go out to a depth of 30 feet below water surface, so way offshore. So these are truncated just in the near shore zone. But if you notice, these are elevations in feet. This beach grew something around 18 feet vertically. So a tremendous amount of sand was deposited. And if we step through that, we can see here is the beach in 1988. Here is the beach in 1997. In 1997, recall, was that little bit of high water period. So the beach gave way to 1988, where it gave up the subaerial part of the beach and stored that offshore in sandbars, with, again, the purpose being to be able to trip those big waves coming in and lessen their impact on the beach. 2000, it had grown again. And by 2008, again, about halfway through that period of low water, it had grown to this substantial amount, again, about 18 feet vertically and growing some 250 feet horizontally. Funding for shoreline damage studies kind of tracks water levels. When water levels are high, there's plenty of research money to understand how this works. But in 2008, and the beach had been growing for about 8 or 10 years, there was no money to continue these surveys. So this is our last survey. This is that same location today. And if I may just hop back here for a moment, I want to show you in this picture, here's where the pipe comes out. Here's the telephone pole. That new dwelling that we're looking at is going in right here in this particular location. So in 2018, the house was under construction. You can see that they're working on the deck, on the roof of the house. Here it is in 2019 with a bigger revetment. A few rocks became a revetment out in front of the structure. And here it is this year. Tremendous changes. The beach has receded even further than it was in 1988. It's given up more territory, and the story is not over yet. So in terms of softer solutions, I'd like to direct you to the website at the bottom, the Cape Cod Coastal Planner. For the Cape Cod region, they have done a tremendous job in evaluating all types of shoreline soft solutions as well as hard solutions. If you click on any one of these, and here's another few examples of these, the website will provide for you both the pros and the cons, approximate costs for each of these types of actions that can be taken along shorelines. And again, some of the interesting ones are beach nourishment, replenishing the beach with natural sands, elevating structures to be more resilient, or actually relocating structures that are in danger. And again, many of these things can be incorporated into master plans. So I'll end there and thank you very much, and glad to answer questions, and I'll turn it over to the next speaker.
Okay, guys, should I go ahead? Jennifer, is it anything to say before I start? Hearing none, I will go ahead and share my screen. Okay, can everybody see that?
Yes, we can see it. I'm sorry, I was having difficulties on muting myself. So
That's fine.
all
Okay,
set.
so-
Go ahead. Thank you.
Super. So now I want to take all the good information you just heard from Drew and from Guy and put that into context for what do we do about it? How do we respond to this? So I'm going to take all of their really nuanced analysis and just draw some fundamental points to put on the table for everybody to just think about. The first, drawing from Drew, is that you ought to recognize that the lake level fluctuations are predominantly a natural process. We have very little ability to control them through engineering solutions. I know folks are talking about dredging and opening up channels or doing better management of dams, and there's just a very limited ability for us to change water levels, especially on the upper lakes. So nature is a dynamic force. The second thing is, drawing a bit from what Guy pointed out, is that the wave energies, particularly when lakes are high, are just remorseless, pounding processes that are going to just keep working away at any kind of structure that we put on the shoreline to try and stop that process. So it's almost a losing battle from the start. When you start trying to put in structures to fight them, the lakes are going to overcome that eventually, unless we start to put a whole lot of money into continually updating those structures and maintaining them and improving them. And that means whenever you start heading down the road of armoring, you're heading down the road of long-term ongoing costs to maintain them. So that's another consideration. And then finally, the point I'll draw is that unfortunately, and kind of an unhappy irony, the places that are most desperately to armor the shoreline because they're experiencing the highest rates of erosion are also exactly the same places where erosion structures do the most damage, because they're so dependent on the erosion coming off the bluffs and beaches behind them to replenish the sand supply to keep that beach natural. So if you armor, the more effectively we build armoring structures, the more effectively it stops that kind of natural process that Guy described of the lakes getting broader and emptying in. And so the more eventually you're going to lose your natural beach. And that may take a few cycles of the lakes going up and down, but that's kind of the long-term process that we're heading at. So I think I've listened to Drew and Guy speak enough. I think I can make those claims to set up the stage for what do we do about it, and they can correct me during question and answer if I got it wrong. Let me, okay. Well, I'm having trouble advancing my screen. Let me try this again. Okay, there we go. So just to quickly say, the work that I'm presenting along with Guy is a research program that we've been working on with funding from the state of Michigan's Coastal Management Program. It's a participatory action research program. So we've been working closely with local communities around the lakes to try and figure out how we can develop, use off-the-shelf data sources and really straightforward analytical processes to help communities understand the dynamics that they're facing and better plan for them. So this is the team we've been working with. So just to give that acknowledgement. Now, I talked about those natural systems in my summary of Guy and Drew's insights into the natural systems. Let me talk a little bit about the legal system that we're dealing with. So on Great Lake shorelines, we basically have three common law constitutional doctrines that are at play here. One is the police power prerogative that the states enjoy and that they delegate down to their local units of government. The other is the public trust doctrine that speaks especially to shorelines along the Great Lakes and ocean coasts. And then the third is the private property rights doctrines that are protected through constitutional protections. So just quickly, the police power is the power that the states have to protect public health, safety, morals, and the general welfare. So that's the authorities that states have to adopt environmental protection laws or to develop programs that benefit the public. And they're viewed expansively by the courts. And the government, the states have generally delegated a lot of those authorities down to their local units of government. The second authority is the public trust doctrine. This is an ancient common law doctrine that goes all the way back to ancient Roman law. And it's based on the notion that some things are common to all: the air, running water, the sea, and the shores of the sea. All of the 8 Great Lakes states have adopted that doctrine as well as the ocean coasts, because they recognize their Great Lakes were more like oceans than they were inland seas. And that means that we have a public trust interest in some access or use of the shoreline. And I'll talk more about that in a few minutes. But the thing to know is those 2 doctrines are what gives the state of Michigan and its localities the ability to have programs and adopt regulations that are designed to protect the natural shoreline. Set against that, to make sure that the government does not abuse us when it exercises those authorities, are our private property rights. And those rights, you should know, when we say we have private property rights, it means we have the right to reasonably use and exclude our property, particularly as against governmental abuse, against government doing things to us without having a good reason to do it. It doesn't mean you have the right to do whatever you want with your property, even if it damages your neighbor or creates a public nuisance. It gives you the right to reasonable use and expectations. So those are the 3 doctrines at play along the shoreline, and then they've been converted in some ways into statutory law. So just quickly, for our purposes, that means the localities, local governments' planning and zoning authorities, our ability to engage in planning and then adopt zoning to implement those plans. The State Submerged Lands Act and the high-risk erosion area programs that is really the source of authority for that is coming out of the public trust doctrine. Protections that are built into those planning and zoning statutes, and our federal and state due process and regulatory takings protections that make sure that government doesn't go too far. Okay, so one of the problems that we deal with on a Great Lakes shoreline is that this public trust notion all is kind of hinged on the notion of an ordinary high water mark. You have to start drawing lines when you establish laws that tell you where you can do things and where you can't, and where boundaries exceed. That turns out to be a bit of a challenge on a Great Lakes shore, where it's not tidal like the ocean coasts are, but nonetheless fluctuate pretty dramatically up and down. So in Michigan, when you own to the water's edge, if your parcel gives you the right to own to the water's edge, you own all of that property to the property's edge. The state and the localities have the ability to regulate your use of that property through its police power jurisdictions. And there's this public trust right that comes along with our public trust beaches that our courts have ruled gives us a right to use the public beaches and imposes a duty not to impair them. So for some stretch of beach, there's an overlap here where you have both a private ownership interest and a public trust interest overlapping. And it falls somewhere in here where the dry beach, wet beached, and submerged lands mixes. So the question is, well, where on Michigan's Great Lakes beach, where does that ordinary high water mark fall? And through court decision and regulation, we actually have 2 ordinary high water marks now. One is the natural ordinary high water mark that was set by the Supreme Court in its Glass v. Gokul decision in 2005. And the court said, people have the right to walk along the beach up to the point on the bank or shore where there's precedence of continuous water in the past. So basically, that's what gives folks the right to walk along the sandy beach. So if you're a shoreline property owner, you own to that property, but this is something like someone having a right to walk on a sidewalk in front of your house. That's what gives folks the right to stroll. I usually tell them strollers, but that doesn't give you the right to have a barbecue or a picnic on somebody's front lawn in front of their beach. So, use it to stroll, but use it with respect to the property owner. So that's kind of the balance that we've developed in terms of our use of the shoreline through the natural ordinary high water mark. The second ordinary high water mark comes through a set of elevation-based standards that kind of speak to what Guy was talking about. The idea being you draw a horizontal line along the water's edge, and where that line hits the beach, that's the regulation-based ordinary high water mark. And lakeward of that, the state has an interest. That's where the state's permitting authorities kick in. And landward of it, you may be regulated by the local government through zoning, but it's not a state permitting interest. The problem with that elevation-based standard is it turns out to be actually quite dynamic for reasons that Guy just explained. I don't think it was thought through when they adopted those regulations in the 1960s. And that's proven to be a real difficulty for shoreline protection purposes. The other kind of shoreline standard is the erosion risk areas that are determined by high risk hazard lines. So basically, any part of the beach that's subject to this elevation-based standard or the high risk erosion area is where we have state regulated beach and where you have to get a permit from the state and probably the Army Corps of Engineers as well. So those are our two watermarks. That's where we start drawing lines. So given that, in the short term, the question becomes, well, these are highly dynamic systems. What are our options for addressing these high rates of erosion that Guy talked about in his presentation? And basically, we have three kind of basic approaches. And those include first, I'm sorry, I'm skipping ahead. I can't see actually my whole slide. The other point I wanted to make about shoreland ownership is that when you own on the shorefront, you own what's referred to as a movable freehold. So under our common law public trust doctrines, when the beach grows through accretion over time, you automatically gain more beach. You're gaining beach at the expense of the state. Those submerged bottomlands that are owned by the state become sandy beach that's owned by the property owner. But by extension, as erosion takes place and inundation takes place, that ownership interest automatically transfers back to the state. So you lose some of your property. So if you bought shoreline property that's right on the shore that's eroding over a course of a foot a year, you essentially bought diminishing property, naturally diminishing property that's naturally transitioning from private ownership into state ownership because of these background erosional processes on the operation of the public trust doctrine. Okay, now I jumped ahead, but let me talk quickly. So given that, how do we plan for community resiliency and what does it mean to be resilient? And basically resilience, this is repeating a little bit what Zach pointed out earlier. It's figuring out how to respond to shocks to the systems, kind of sudden weather events that cause severe storms or flooding or high erosion events, and then longer term stresses, the longer term background erosion rates, for example, that are occurring, or the movement of dunes over time, which is a natural process as well. For the Great Lakes, that means we're mainly worried about water level fluctuations and storminess, as Drew and Guy just talked about in detail. Okay, now here's where I thought I was. So three basic approaches to that, and there are actually more than this, but at core, there are three basic things we can do in the near term, given these highly dynamic systems. The first is to armor. Put in structures that are designed to stop these erosional processes. The second is to nourish. So this is dredging sand from a harbor and putting it on the beach. Some communities in Michigan, this is St. Joseph, is kind of enjoying the benefit of the Army Corps of Engineers dredging program to keep the river clean there. And they're able to take some of that sand and basically nourish some of the city's beach. So that's helping them preserve their beach through a beach nourishment project. There are currently nobody that I know of is dredging from the deep water in the lake onto the beach. It might be a possibility. That's something to talk about with the state regulators, but to do that, you have to be able to demonstrate that you're not going to cause long-term damage to habitat or to draw sand that you need to be maintaining the beach, as Guy described from the nearshore region. The third large option is to relocate, to recognize that nature is this dynamic force, and maybe the best thing to do is pick up your home or other structures and move them back. Now, in between these three basic functions, there also may be the possibility for some temporary structures like huge sandbags. The problem there is they may become permanent or they may dissolve pretty quickly, or maybe elevating structures to get them up above inundation levels. The problem with that is it may not work so well on a highly eroding beach, which means you would just have a beach house on stilts out in the middle of the lake. Let me just quickly step through these three sources and give you some of the pros and cons just to put this in context. So the idea behind armoring is to slow erosional processes. You can't really hope to stop them permanently because the lake is just going to keep pushing on them over time and they'll eventually give way. Same thing with nourishment. You're basically slowing erosional processes temporarily by putting sand on the beach that will be there until probably the next storm. The primary purpose or pro of relocating is you're conserving the natural beach. But that comes with some cons. If you're armoring the structure to slow erosional processes, you're probably over the long term going to lose the natural shoreline and very likely going to lose it and then lose the public trust beach. If you protect the beach by nourishment, that may be very effective in the short term, but it doesn't last. That sand is going to get pulled back into the system, and it could be a single storm that may take a whole lot of money spent dredging and pull it back out into the water. And then relocating does come at the cost under this the public trust doctrine of the cost and expense of picking up a home and moving it back, and maybe the long-term loss of the land itself to erosion into the lake. So you can think about that too from a private property owner's perspective. Here, their trade-offs are trying to safeguard buildings, but that comes at the cost of the structure that you have to install and the fact that you're going to probably lose the beach in front of your home. You could probably look into maybe doing a nourishment project to safeguard your buildings again, but then that becomes very expensive and it's not clear that it's feasible depending on where you are. Relocating safeguard your buildings by moving them out of harm's way, but again, that comes with the cost of picking up the home and the longer term effects of relocating away from the shore. And then from a public perspective, armoring is designed to essentially protect private properties, but that's coming at the cost of losing the beach and the potential future costs of having to maintain those armorings, which I think is a very real feasible possibility. As folks say, we can't afford this, government, please help us pay for this. Nourishing is again designed mainly to protect property and infrastructure, but it comes at the cost of nourishing and the feasibility of finding a sand source. And then relocating protects property in the form of the structures by moving them out of harm's way. But you may be losing the beach over the long term to erosion. The natural beach will still be there, but it'll be more landward of where it was. And some local governments are concerned about losing revenues because they're losing that shorefront property, although I'll suggest that you don't really lose that shorefront property, it's just effectively moving landward. The bottom line point I want to make out here is there is no easy solution in these settings. If you're in an area, especially of a coastline that's experiencing high erosion, there's no happy answer. Somebody is going to be unhappy because we're trying to protect something that's bringing an expense. So don't think there's a silver bullet solution out there that will let us solve all of these problems simultaneously with a happy outcome for all. I don't think that's possible in a lot of these settings. So that's the short-term response. What do we do in the long term? Well, let's start thinking through better the consequences of the decisions we're making. And I'm going to just step through these processes really quickly. And if you decide that you're looking for help from the Tip of the Mitt folks and from Leah, this will be the kind of work they can help you figure out with your community. Basically, what we've developed with the research funding support we've gotten from the state is a decision-centered scenario-based planning approach. What that means is we're setting possible futures against possible management options and then trying to figure out what are the different outcomes that a community might experience and how might they plan for them. So the climate futures we're looking at are a lucky future where lake levels are low and there's not much storminess, an expected future where lake levels are close to their long-term average and the storminess is average, or the perfect storm when the lakes are really high and they're very stormy, kind of like Guy described we're experiencing right now because the lakes are so high and that's when the storms get really bad. You can then turn around and map where how those climate futures translate into space on the ground. So the areas in yellow are going to be underwater during a lucky storm event. Again, that's lakes are low, not too stormy. The burnt orange areas are potentially flooded or hit by high energy waves during an expected storm event. So close to average water levels in a 100-year storm. The red perfect storm is, oh my gosh, the lakes are really high and you're getting hit for the storm. One thing to note here is there's definitely risk for shoreline structures right on the lakes, but there is a huge amount of risk as well for inland structures along the riverine system. So if you're a community that has a river draining into the lake, you may actually see as much or more damage, potential damaging coming from storms in your riverine settings as on your lakeshore settings. Once we know where those high hazard areas, then we can map what you currently have, what your current structures are. This is the city of Grand Haven, by the way. The middle image is just to show where we think buildings might go if this community develops fully under its current zoning code. So lots of potential development still in the city of Grand Haven. And then what we did was say, well, what if we adopted some basic setbacks that set structures back away from high hazard structures? And so the main difference between these two images is we're still allowing a lot to develop in the city of Grand Haven. We're just saying, but maybe don't put it right next to the water's edge. And when you do that, now you can analyze, well, what are the implications, either in terms of the land area affected, or the number of structures that could be harmed, or the fiscal impacts to the community, comparing the loss of revenues and the damage that's going to happen from cleaning up the mess. And pretty much every place we've done this analysis, what we found is if communities stay at their current conditions, they're definitely going to see some bad impacts if a perfect storm hits. But man, if they get anywhere close to building out under their current zoning, they're going to see a huge increase of properties at risk and huge amounts of damage that could be affected during a perfect storm. But if they adopt some simple setbacks, easier said than done, but setbacks and other BMPs, they're not going to eliminate all the risks totally. You can't live in the world and not experience some risk, but they can greatly mitigate or adapt to the risk that they're confronting in the future. So adopting some basic, identifying where your high hazards are, taking a sense of how risk adverse you are and where you think it makes sense to grow and where it doesn't make sense, and then maybe adopting some really basic setbacks might go a long way to helping your community become more resilient to these kinds of structures. And then you might add to that vulnerability assessments, and I'm not going to speak too much about that, but that's basically taking the kinds of analyses I'm showing about where are there areas and structures at risk, and then also thinking about how vulnerable are the people in those places, either because they're lower income or they're elderly, and so they're potentially much more affected by these kinds of impacts, and folding those kinds of considerations in as well. Okay, so once you do that planning and now you've substantiated what you think as a community you should be doing, and you need to have those conversations in the community to think that through, then the two primary mechanisms to approach are to start doing low impact infrastructure development, and that's basically managing water. So one of the goals here is to try and manage water so that it's not rushing off the landscape in places that do harm, but is infiltrating the landscape as much as possible. So get rid of curbs and gutters and start putting in rain gardens and that kind of thing, but don't do that right next to the water's edge because you might exacerbate erosion. The other is to start thinking about dynamic coastal shoreline zoning. And this is a zoning code that the city of St. Joseph adopted after that house got built. That's kind of the poster child of a house that the homeowners kind of ignored the city's advice, decided we want to be close to the water. They built that house. That prompted the city to do a study and say that really wasn't a good idea. You can see now the line they adopted, that's the setback they adopted. And if you recall the picture that I used to show the idea of moving back, that was the house. That was the house. Those folks picked it up and moved it back to get it out of that harm's way. We'll see over time if that was actually moved quite far enough, but at least for the near term, they've done that. And part of the reason they did that was because the city did not want them to install armoring right there, because they knew, and the neighbors knew, that was going to start to exacerbate the erosion that's happening in that larger area. So at the end of the day, you have to make difficult decisions, given that there are no happy answers sometimes to how to balance things. And adopting setbacks and putting property owners on notice, the time might come where you have to pick up your house and move it. Maybe a decision that you want to make. If you make the decision, nope, we're going to let folks armor to protect their beach house, then you need to understand that you're probably setting yourself up to eventually lose that stretch of beach, because putting that armoring structure in ultimately starves the sand supply that's needed to maintain a natural beach over time. And that has implications for both the locality and the larger public trust. So let me just draw some quick concluding comments, and then we'll go to question and answers. Here are some challenges that we're confronting. There is a new normal. I know the notion of climate change has become contentious, but the reality is, for whatever reason, set that aside, we're seeing greater storminess and we're seeing greater effects from those storms when lake levels are high like we're experiencing now. And we need to start planning for and adapting to those situations. We're seeing huge disconnects in how we're thinking about problems. The lakes, to the extent that we're armoring them a little bits at a time, we may be heading towards a death by 1,000 cuts. We may be losing long stretches of our Great Lakes shoreline, not all at once through one huge massive armoring project, but by the accumulation of 1,000 cuts of armoring, if you will. And then boiling frogs describes the notion that, you know, supposedly, I haven't tested this, if you put a frog in a pot of boiling water, it knows it and tries to jump out. But if you put a frog in a pot and slowly boil it, the frog will boil to death without knowing what's happening. So again, I don't know if that's really true, but it's a metaphor that kind of illustrates when these changes are occurring in a way that are easy for us to dismiss, we don't often realize what's going on until we stop and think carefully about it. The other challenge we're facing quickly is that we've just become incredibly polarized politically, and that's not helping us engage in the difficult conversations that we need to be having. So we need to try and figure out how to get over that. We need to get around the idea that there's a one-size-fits-all silver bullet out there. I don't think we should be thinking that it's possible to design armoring structures that will solve all of our problems in every place. But it may be the case that we decide there are places where we really should armor, knowing that that could result in the loss of the shoreline because of other larger considerations. So there are probably going to be multiple solutions, none of which is a silver bullet, but all of which carefully weigh and balance the costs, the benefits and the costs. I think we're very much facing a challenge right now with underinvestment in government. It's really hard for local governments to engage in these kinds of analyses because we've just become so adamant that we don't want to pay any more taxes for government. Well, you get what you pay for. And if we're underfunding government at all levels, it's not surprising that government then is incapable of doing the kind of work it needs to do to really make sure that things are happening the way they should. Unfortunately, I think we're setting up some unfortunate policy expectations. If we decide we're going to always let everybody armor whenever they decide they need to armor, then that may be setting expectations that are creating a long-term default decision that we haven't carefully thought through yet. At the same time, if we decided we're never going to ever let anybody armor, that would kind of cut in the other direction. So again, here's my plea for us to slow down a little bit and really take care and think through the implications of the decisions we're making. And then finally, there's a real problem with loss aversion. Human nature, once you've built something, you really get attached to it and you so demand that you protect it, even when you recognize that maybe that's not the wise thing to do. And there's a whole lot of that, I think, that happens when we build too close to the shoreline, and then we want to do everything to protect it, even when it's so clear that maybe over the long term, that's just not the thing to do. But having said all of that, we can head in the right direction. We need to engage better participation and planning before things happen. That's what the tip of the mitt is all about, and what Lee is standing ready to help you do through the planning processes. We need to absolutely make sure that the government we have is really good government, make it as transparent and effective and well supported as possible. We need to start thinking about adopting landscape smart policies that really take into account the kind of natural dynamics that Drew and Guy laid out for us. We need to be thinking about no regrets policies. Hey, maybe this will make us a better community, even if it turns out to be not as bad as we thought it would be, but we're still moving in the right direction. We need to definitely learn to live better with nature. Rather than thinking that we can fight nature, nature is going to overcome. It's just such a powerful force. And then finally, we need to rethink our economics to focus more on a stewardship of the resource base, recognizing that at the end of the day, it's really the base of the economy that we depend upon. A good economy depends on a good environment and natural resource base supplying it from underneath. So kind of shifting our thinking a little bit that way. So that was really a whirlwind tour of what you can be thinking about for your planning and zoning endeavors and infrastructure endeavors. But I hope it kind of puts things in context given the science that we got from Drew and Guy. And so I'll finish off here and then we can open the door to questions.
Great, that is wonderful. And so I think we will go to question and answer. So if all of our panelists want to come back to video. And again, for those of you that are watching, you can ask questions by either submitting them in the Q&A at the bottom of your screen, or go ahead and raise your hand and I will call on you and you can unmute yourself. And so the first question we have says it was noted, and I think this was from Guy, that our shorelines are more stable in Emmet and Charlevoix County and not so threatened by erosion, but inundation. So are there some BMPs that are better than others in this case? And if so, what are they? And
Is Guy still on? Oh, is Guy still on, or did he end up having?
it looks like we lost Guy.
Oh, it sounded like he had kind of a bad internet connection. He might have lost his connection.
Yeah.
Let
So
me
I don't
just
know
say,
if one of our other speakers can.
yeah, I can say a few things, and then if Drew wants to add to that. I think it's correct, and that is good news for your area, the tip of the Mitt. You seem to have more stable shorelines than what the folks to the south are really suffering. You do have places where there is still some erosion taking place. So the first thing you're going to want to do is take advantage of that website that Guy provided and the other analyses that we provided to figure out what's the state of your shoreline, and really plan for that. And then the second thing is, even if you're facing inundation, you still don't want to be too close to the water's edge. And you want to be thinking about those best management practice, water management systems that I talked about in that guide show. So you might be better able to take advantage of the soft shoreline armoring options where you are, that would work better for you than maybe down south where the energy system is just too high.
Okay, and Guy, you just reappeared. We lost you for a minute.
Sorry about that. I did.
That's okay. So the question that just came in was that Emmet and Charlevoix County seem to be more stable and not threatened by erosion, but inundation. And if so, are there better BMPs that could be recommended for inundation? And if so, what are they?
So, as Dick indicated, in the drowned river mouth valleys, that there is a tremendous potential for flooding, not only from static water levels, but some of the dynamic things that happen across the Great Lakes, the movement of storm systems that push water against the shorelines. So the types of things that Leah and Dick have been doing in terms of best management practices for looking at where those structures could be vulnerable is definitely a good thing to do. The types of mapping that they're doing with digital elevation maps and identifying structures are something that a community can do anytime, not necessarily during the high water times. They're not limited to that. So it's a good long range planning type of effort.
Great. Another question that I have is, what should property owners do when their neighbors get permits for work that could impact them, as far as revetments or some of the other armoring options that were talked about?
So again, the state regulatory folks seem to look at one individual property without a tremendous amount of concern for the neighbors. So unfortunately, the burden falls on the neighbors to try and negotiate some sort of settlement with the property owner in terms of how to build structures and to recognize that there will be downdrift impacts. Unfortunately, there isn't any other remedy right now other than that's been a big driver in trying to educate coastal communities as to what these downdrift effects are. And again, during the time after the 1986 high water level, we did a number of field studies for the state on shore parallel structures and shore perpendicular structures to document scientifically just what the impact of those structures are, and it can be very catastrophic. It's all any property, and then several months through the fall period, and the downdrift erosion from that groin. I'm still with you. I'm getting flash here.
Yeah, I got your internet.
Yeah, you're cutting out.
Yeah. Let me, if I can
I'm sorry. I do live in the U.
Living in the UV, yeah. So,
Yeah.
Dick, if you want to take over.
Let me put some words in Guy's mouth and he can tell me if I got it. I think where I was headed is that you have to pay close attention to the effect that a structure that you want to build will have on neighboring property, and it will very likely have some effect. That there's just no way to design a structure that doesn't come without risks of changing the sediment patterns. So from my perspective, unfortunately, that's led, one solution is for groups of neighbors to get together and just build a bigger, longer armoring structure, which then kind of protects them from high erosion on their neighbors, but it just extends the longer term impact that those armoring structures are having yet on further neighboring properties and the movement of the sand on and off shore. So it's kind of heading in the wrong direction in terms of the long-term impact to the shoreline. There is some, I have heard some folks assert, we can build these structures and the lakes will, when the lakes go back down, that sand will get pulled back on from the offshore and they'll just get covered. And when I've really chatted with Guy about this, what I'm hearing is that may happen for a cycle or two as the lakes go up or down, but ultimately, if you're effectively starving the beach of the sand it needs to replenish itself through erosion, there's not going to be any sand in that nearshore area to come back. So eventually you're just going to end up with a big seawall and nothing in front of it until it gives way, because the lake is still continuing to undermine it and pull it out to the lake. So then you have a whole lot of debris in the lake, which you can see good evidence of if you look on Google Earth now. Lots and lots of debris on the lakes and structures that failed and didn't survive. And I'll make one more point is if all of that doesn't work, then we're heading towards litigation. If you're a property owner who is next to someone who's armored and they've created an accelerated rate of erosion on your property, you might actually have a nuisance claim against your neighboring property owner. Now that kind of claim has not been directly litigated anywhere I can find in the state of Michigan. But it stands to reason that the courts would probably recognize that at the very least, if you're exacerbating your neighbor's erosion, that could be problematic. There's been no litigation either. I'll just tell folks on the idea that if we're letting everybody armor and we're destroying our natural beach, that there's a public trust case there that might be litigated too. That's not been litigated anywhere in the courts. So we're kind of making decisions in a whole lot of legal uncertainty at the same time that we're making decisions in shoreline dynamic uncertainty, at the same time we're making decisions on lake level fluctuation uncertainty. So, decisions that are going to have really long-term consequences and are probably going to be really costly. Guy, did I get that right? Did you catch what I said to it when you come back on?
Yep, well done.
Jennifer, I'd chime in a little bit and certainly say from the perspective of what's happening right now today, planning and zoning don't necessarily offer a bunch of immediate or quick answers, but these are the exact kinds of conversations that we're hoping that local governments and communities can have to try to figure out and appreciate that these cycles are going to come again. And it's top of mind now for a lot of property owners and a lot of communities, given the record high levels we're seeing on Michigan and Huron right now. But that, it's likely that those water levels are going to go back down again too, and we're going to experience another period of low water. So the fact when good municipal planning and zoning, we hope right now, while it's top of mind, will better position communities 10, 20 years down the road for the next cycle, whatever it brings. And that's the critical part of right now, I guess, is making sure that those conversations are happening and all of us start to understand better those natural cycles, the implications of our battles with or cooperations with those natural cycles, and helping communities make those decisions that over the long term will make us all better able to respond and weather these highs and these lows.
Yeah, and unfortunately, I like to say it's the case the lakes seem to go down just long enough for people to forget. So if we're fortunate, as Guy and Drew seem to think that the lakes might be heading back down again, don't think that we can now just walk, forget about all this, that it's gone away for good. And we'll see things come back around again. So we need to really make for good planning now to keep that going.
Great. And for everyone watching, Matt hasn't introduced himself. Matt is with Leah.
Yeah, sorry about that. Matt Cowell with the Land Information Access Association. Thanks,
Great.
Jennifer.
Yeah, thanks. And so we do have a question from John Froberg. So I'm going to go ahead and unmute you and make sure you unmute yourself. Go ahead, John.
Yeah, hello.
Yeah, we can hear you.
Yeah, hi. So I have a lakefront property in Dunewood and Bridgman, 12 miles south of St. Joe. And I've been witnessing the mess they've made out of the lakefront in Stevensville, just to the south, as well as, south of the pier in St. Joe, as you know. And then we have the Cook Nuclear Plant, which has a steel wall on the southern end of it that is now in the water, with a boulder revetment on the northern end of that. And it's obviously eroded from that to some old revetments in Wildwood, all the way on down to a pile of rocks in northern part of Dunewood, where the 6 property owners in a row are planning to put in a revetment, which will be 100 feet to the north of my property. I'm wondering how, as I'm watching these things go in, they're pretty much throwing the public trust doctrine out the window by building these things into the water. You cannot walk the beach at all anymore. How is that happening? What happened to the public trust?
Yeah. So let me just say the public trust doctrine is not a self-executing doctrine. It's a doctrine out there that exists through a combination of the state's common law and its constitutional law and the Great Lakes Submerged Land Act. And then the state tries to implement it through its permitting program, but it takes people engaging on that doctrine in that permitting process and maybe through litigation to strike the balance that's happening. The state, I know the position they've taken is that they favor anything you can do short of armoring first as a response to a highly eroding shoreline, but at the end of the day, they're not going to stop someone from armoring if they need to. That hasn't been litigated. I think you can make a case they're not actually protecting the public trust fully by having made that decision, but we won't know that until if and when that gets litigated and it goes up to the Michigan Supreme Court. And it's part of the reason they push back is I think they're doing that with the belief that when the lakes go back down, the beach will come back, and so it's not a long-term impact. And that may be where our better understanding of science today may need to inform our long-term thinking on how that legal doctrine plays itself out. So it's a really good example of, honestly, that vindication of the public trust, or what it really means, may not happen until someone brings a lawsuit and forces the courts to help us think through the implications. I guess the other point I'll make is, I know they have to get permits for that, and my understanding is Eagle has to consider local concerns and such when they grant permits. So you'll want to make sure that you're giving feedback to the permitting folks so that they're aware of what's going on and give them the opportunity to respond to that. And
because they all want the revetment to protect their septic fields, afraid their house will be condemned. So I had a walk with Nick from the Berrien County Health Department, and he said all of these septic fields can be easily moved and reconfigured. And, that's my only hope in preventing them from getting permitted. As soon as I understand I can't do anything until they actually apply for the permit with Eagle. Is that the case?
Well, I think you can be conveying your concerns to the Eagle staff right now. They won't kind of formally put that into their decision-making until the permit request is made, but I think you can certainly be communicating with the staff right now.
Right. Okay.
So and I'm happy to chat more offline. And it looks like, Jennifer, you've got other questions coming in, but
yeah, there are other questions.
Thank you very much. You guys are great.
But thank you, John. And yeah, you can reach out to any of us after the fact. So another question was on inland lakes such as Lake Charlevoix, can bioengineering the shoreline by building a natural man-made berm into the lake and plant with native deep-rooted plants work to maintain the shoreline? And in terms of zoning, can a shoreline protection or greenbelt move with the high water mark?
So there, I'll make a first cut and then Guy and Drew step in. The inland lakes do not fluctuate like the Great Lakes do. So at least not as dramatically in the way that we see the Great Lakes move up and down. Although I recognize a lot of them are really high right now.
Lake Charlevoix is connected to Lake Michigan.
So for those areas, yeah, they become part of the inland lake system. And I do think there you could probably, because the wave energy is lower, Guy, I'm getting out of my depth here, if you pardon the pun. But I think natural protection is probably going to be more effective there because it's not going to be as likely to be washed away. And definitely there's where you want to start thinking about trying to move structures back so that over the long term you can you maintain to enjoy it, but not be in harm's way in the structures that you've got.
And I would say yes. The Watershed Council promotes bioengineering on Lake Charlevoix. We have a landscape engineer that actually does designs and can recommend firms. And you can reach out to the Watershed Council, and we can assist with that process. I believe Lake Charlevoix, at least part of it, if not all of it, does have some green belt. As far as it moving with the high water mark, the high water mark doesn't move. It's a zone. The water level moves, but the ordinary high water mark doesn't. So, but again, the Watershed Council plans on working with the municipalities around Lake Charlevoix with Leah and all of the partners on the call to see what we can do to improve some of the protections and see if we can address some additional measures to provide additional protections, including promoting bioengineering and buffers. Another question we have is there are dunes in northern Michigan, and the Critical Dune Act was weakened a few years ago. Has anyone studied whether that has made a difference now that high water has fluctuated from low water so quickly? So anything else since the changes have been made? So has there been an impact? And I'm not sure any of you guys can answer that. A lot of the local municipalities got rid of their local dune ordinances as a result of the state changes to the dune policy or the dune law. And now that we're seeing high water levels, has that resulted in impacts to our dunes?
The answer on impacts is yes, but again, the only thing that the regulatory folks can do is what the state laws require. So again, the weakening of the Dune Act is going to have a long-term impact, even if it's not visible right now on the dunes. So that is, in my opinion, a step backwards.
Yeah, I guess that kind of speaks to the idea that I didn't make this point earlier. We talk about hazardous events or disasters, natural disasters. Planners like to say there really aren't natural disasters. It's just nature doing what nature does. Where they become disastrous is when we build things too close to areas that are at risk. And so the disaster is the loss of the built structures and the investment that we put into it. So it's not kind of nature taking something from us as much as nature doing what nature is going to do. It's in retrospect, us having done things in places that wasn't a prudent place to go. The Dune Act was weakened. It's allowing more development to happen in the dunes than what could be permitted before. That could end up letting people build structures in places that in the long term turned out to not be such a prudent thing to do.
Great. I have one more question, and it is about the different treatment or options that were discussed. Is there a cost comparison between shoreline armoring and moving homes?
There is, and we just recently got some numbers on that from a webinar that the state held. The cost is about the same per linear foot of shoreline of armoring versus moving a house. So they're very compatible.
So you should definitely look into, if you've got a structure with a septic field in front of it or the structure itself, you really should be looking at moving, because in the long term, that actually may be less expensive to you than trying to build up an armoring structure to stop the beach from doing what the beach wants to do.
And on that note, the Watershed Council has publications available on our website that we specifically have a publication that deals with home moving that talks about the costs associated with that. So that's available for any of the participants that are watching. And with that, it is 2 o'clock and I want to be respectful of everyone's time. So we are at the end of our webinar today. I want to again thank all of our speakers and presenters and partners very much. I apologize for the background noise. But I also want to give a special thanks to our funders. Again, the Charlevoix County Community Foundation, the Petoskey Harbor Springs Community Foundation, the Michigan Coastal Zone Management Program, the Michigan the Michigan Department of Environment, Great Lakes and Energy, the National Oceanic and Atmospheric Administration, the U.S. Department of Commerce. And I thank you everyone for joining us today. I hope you found all the information and dialogue valuable. Again, all of the partners, thank you very much. Feel free to reach out to myself or the partners. We'll provide a recording of the webinar and the slides at a later date. And with that, I hope you have a wonderful day and stay safe and stay healthy.
Thank you all.
So, thank you.
Thank you.